My name is Alexey, and you probably heard of what I was doing. So this is TurboGet. It's just a fork of Go Ethereum, which has been taken like in December 2017. And since then, I tried to experiment. So at the moment, I still see it as an experimentation project, although I do want to release some working version, which is not far away, I hope. And I wanted to say that I like giving these talks, although I don't do it very often, because it makes me document my ideas a bit better. So I want to mention that this work has been supported by the grant from Ethereum Foundation, and thank you very much for that. So first of all, what is this TurboGet and why did I start doing this? The motivation changed a little bit since I started, because now I see it as a client for infrastructure providers like Infure to people who want to run full nodes and archive nodes with the history, potentially exchanges or miners, or people who don't just want to sync up to the blockchain and start sending Ether or receiving Ether, but actually people who want to run the infrastructure nodes. And that's why there's a lot of focus on, like, for example, disk space consumption and the sync performance. So this is the shortly outline. I will skip very quickly through the things how it started, because I already showed it in Toronto. And we're going to skip quickly through authenticated data structures. There is a little bit more there than last time. Then we compare how the state is persisted in Geth and TurboGet. This is the crucial bit. This is where the biggest difference is. Then we're going to look at some alternatives to the Patricia tree, which exist in some products and don't exist. There's some of them that don't exist yet. Then we will look at the different processing architectures. And here I have included, since last time I have included Ethermint. I will tell you a little bit about this project and why it's interesting in this context. Then we will look at the latest data that I had from the TurboGet nodes. And then we're going to discuss shortly about light clients, because this is something I have ignored largely for a while, and now I started to look into it, like whether I actually be able to support it. And lastly, we're going to look at some future thoughts. This is going to be just the ideas to throw out at you. Maybe you will find it interesting. Okay, so this is how it started. It basically was in November 2017, when the CryptoKitties were very popular. And so it started with trying to profile the Go Ethereum and finding out that the bottleneck was potentially the state operations. And then, so this is kind of the primer for some people who might not be familiar with what is Patricia tree. So essentially, if we want to store the data in tamper-proof manner and then able to prove something about this data, you usually use something like a Merkle tree, which allows you to do the proof of membership, which is showed on the right. But if you just do so here on the left, as you can see that the proof consists of the whole structure, so that Merkle tree solves that. But the Merkle tree doesn't, in its naive version, doesn't solve the problem of proof of non-membership. But if you sort the keys somehow, then you could actually prove non-membership. And then another property we want from such a structure is that as we modify our data structure, we want to encode the modifications in a very compact manner, so we don't have to repeat the whole structure again. So that's another property we want. And you can see that here, the things that are shown on the right are the modifications made to the tree. So the gray bits on the right are not the ones which we're repeating. They just I just put it there for clarity. So essentially, we want to encode modifications compactly, and so one of the solutions to this problem is the Merkle radix tree. So what you can see here is the radix tree of the radix 26. So because it's a Latin numbers, and so you could probably see how we put the words bug, the cat, dog, and things like this. And so the triangles you can see there is that we hash upwards from the bottom. So we concatenate the keys and concatenate the hashes on the bottom and then the hash upwards. So this is So in Ethereum, something like this is used, but not with the radix 26 or radix 4 like in this picture, but with radix 16. However, if you just do the naive radix tree, then you have a problem of these, like if you put a lot of random keys into the structure, you will end up with a lot of the very long segments of these nodes, which are kind of under-occupied. And that's kind of the inefficiency which is solved by the Patricia tree, which is actually an acronym. And so the idea here is that we replace the segments of these nodes with so-called extensions, and then if they leave to the actual values, then we call them leaves. So the leaves here are the diamond-shaped things, and extensions are squares. So in a Go Ethereum code, it's a little bit confusing, but the branches are called the full nodes, and these leaves and extensions are called short nodes. I have also introduced another type of node, which is called a duo node, which has exactly two children, because I've realized that there are quite a lot of them, and there might be some optimizations. So essentially, what you see on the left is that how the radix tree looks like, and on the right how the Patricia tree looks like, with the sum of the efficiencies here. Unfortunately, that comes at the cost of complexity of the algorithms. So if you ever looked at this Patricia tree processing code in any client, you might find it's a bit complex, because you have to handle lots of special cases, as you can see on this picture. Like, so pretty much there will be like a switch case statements, lots of those. And so, as we mentioned, in Ethereum it's got radixes 16, and all keys are, so because in Ethereum, before we add apart from when we store the actual Ethereum state, we always store the keys of 256-bit, which is 32 bytes, which is 64 nibbles. And the reason for that is because all the keys are hashed by the sketchup function, and the reason for that is we would like the tree to be balanced, and we will see why it is important a little bit later. So when we hash them, they kind of start to be randomly distributed around the tree. So this is very shortly to remind you that whenever we talk about any serialization, usually in a Ethereum client, usually it's done by the means of RLP, which is recursive length prefix. It's not very important for this particular presentation, but just so basically the RLP can encode either single bytes or byte arrays of different sizes, or they can recursively encode the sequences of other RLPs. And so now it allows you to sort of understand this sort of persistence. So this is how the Geth and probably most of other Ethereum clients currently store the state in the database. So they store it in the key value store, and so if you look at this Patricia tree on the left, so every node of Patricia tree is serialized using RLP, and that becomes the value in this database. And if you then apply this hash function, then it becomes the key in the database. So essentially, that's very sort of straightforward. And so when we want to eventually, as the block numbers increase during the sync, the Patricia tree becomes really large, and eventually it does not fit in memory anymore. And we will have to offload some of it into disk. So let's imagine that we have offloaded these 3 nodes onto disk, and what we have now in memory is just the hash of this node here. So this one is not in memory. And eventually, let's say that some of our transactions request that piece of state. They need to read it or write it. So what the Geth or other clients usually do, they do the lookup operation. They look up at this hash, and they consult the database and see, okay, so that will be that kind of hash, and they will get back the RLP of the node and then deserialize it, and they will instantiate it in memory, and then they need to go further. So that's going to be one lookup to the database, and they say, oh, and now we need that one. So they will take the hash and do this. So you see in this particular example, there are 2 lookups. And you also need to notice that these lookups, they are necessarily sequential, because you cannot do the second lookup until you have done the first, because the lookup value for the second is contained in the result of the first. So there's a data dependency there. And this is why the depth of the tree actually matters, because the deeper is the tree, the more the more lookups you have to do, and because they're data dependent, essentially you get more, you cannot sort of paralyze it. So remember, depth is important, and this is why, this is actually the main reason I started to experiment with a different database layout, because of this depth dependency. And so here, let's see how, it's like, what is the current depth? Well, this is not really current, it actually was quite long, but I didn't want to recalculate this number. So to get the idea is that, so the levels from 0, so these are the levels of the Patricia tree, and you can see that level 0 to 5 pretty much is fully occupied, which means that all these 16 elements in these branch nodes are all completely full, which is kind of good, because it means that we don't waste too much memory. But then after that, at the level 6, 7, 8, we could see that there's more sparsity occurring. So by the way, in the rows you get the levels of the tree, and on the columns you get the different occupancy levels. So the column number 1 is kind of special, because as you might remember, in Patricia tree there is no branch nodes with occupancy 1. They are replaced by either extension nodes or leaf nodes, because that's the point of this Patricia tree optimization. So what you see in the first column essentially are these the leaf nodes. Most of them are actually leaf nodes. It's like things that are leading straight into the key values, or some extension nodes. And you can see most of them are sitting on the level 7. Which means it's, and after that, like, they all die down after level 9, which means that our balancing actually works. So the hashing of the key actually makes the tree pretty balanced. But as I said before, the depth matters. Now, so let's look at how we do it in TurboGet. First of all, we do not, so one of the leaps, so one of the things that I try to do is that, okay, let's not store Patricia tree at all. Let's not do that, and let's just store the key value, like the accounts or storage indices as they are in the database, as the key value pairs. Can we actually do that? Because there seems to be a presumption that, like, it's going to be too expensive to reconstruct the Patricia tree from scratch. But I thought maybe not. Like, let's try this. And then I tried, and it actually wasn't too bad. I mean, it was a bit of a struggle, but I had to rewrite basically pretty much all the code which does the tree rebuilding, because it wasn't optimized for this specific use case. But eventually I got to the point where rebuilding the Patricia tree is not actually too expensive. The more expensive bit is to actually read it out of the database. So what happens here is that when we essentially, let's imagine the same scenario as before, that this is in memory, this is not, that thing is not in memory, and we only have this hash, right? Or not, actually we don't even need that hash. Yes, we don't. So we don't care about this hash. The only reason why we need this hash, we might need to do some checks. And actually this is what TurboGet does. It actually checks a sanity check that what we actually loaded is correct. But what we do is we say we need everything. We start with the nibble 1. So nibble is a half a byte, right? And so this is the range query to the database, and that range query essentially fetches the first two keys and values. And this is where we essentially just rebuild the Patricia tree and plug it in there. And then on the way, as I said, we hash it, and then we compare the hash to this just to say, okay, so that's fine, we didn't make a mistake. And this was actually quite important for me to debug all this hashing algorithm. The most important thing here is that depth doesn't matter. So the performance of this particular mechanism does not depend on the depth of the tree. Which doesn't mean that you don't, which kind of means that you don't really need to balance it, but if you use that, but yeah, so that's a thing I actually forgot to mention when I was talking about it in DEF CON. So let's just for education purposes, you might have heard, might have seen some of the other things, which is called sparse Merkle tree, which you might as well call binary radix tree, because it's also radix tree, but with the radix 2. So the idea is that so when you want to store the key, like in this example, let's say that we store key 0011, then imagine the tree which kind of the radix tree which potentially contain all possible keys. So in the case of Ethereum, it might be like, how many? 256 bit depth of the tree. Of course, that tree is going to be humongously large, but we don't actually need to store it. And the reason why, let's say that in this particular tree, we only store 2 keys. And everything else is empty. That's why it's called sparse. So what we could do then is, so first of all, we introduce some constants. For the level 0, our constant is the hash of the empty node on this node. It will be all the same. For these little circles, the hash is going to be all the same. So here. So then the empty nodes of like empty subtrees of the level 1, they also the same. So we introduce that constant. So for each level, we have one constant. And the same for the level 2, we have this big constant. And essentially, all we need to encode now is that, so when we have any node here, we just compare, is it like a left or a right side? Is it a constant? Is it our empty subtree constant? And if it is, we don't have to look any further. We know it's empty. Like for example, here, we know that that bit is empty. We don't even need to look at it. And so this is the idea. And I remember that's been right up on the Ethereum research, and I know a lot of people like this structure because it's very simple to implement, and yeah, so that could be. I haven't done any tests, but I really want to make a benchmark about what would happen if we use that instead of Patricia tree. That would be interesting to see if there's going to be any difference. But actually, I might be able to do it quite soon. So then there's worth noting that there are some projects which use self-balancing trees, like the Tendermint has this Alleviate tree built in, and there's also red-black tree. So essentially, they all self-balancing, meaning that they try to preserve some kind of balanced shape during the modifications. And which is cool because then you don't have to pre-hash all the keys before you insert them. But unfortunately they have one disadvantage, that the modifications are not commutative. So if you take a balanced tree, a self-balancing tree, then add the key values in a different order, the resulting balancing tree will be different. So the order of the modification, it matters. And it wouldn't be so bad except for this, all right? So in here, I do actually require that the order of modification doesn't matter. So I can batch them up. I can reconstruct the part of the tree without knowing how the large tree was constructed. So it doesn't mean that this is all lost for these kind of things, but it might require a bit more research. It might be more complicated. So now, let's have a look at the processing architectures. So this is kind of super simplified picture about how, let's say, Geth is going about processing blocks. So here you've got a virtual machine, which is essentially like some kind of opcode interpreter. It can interpret opcode. Sometimes it accesses a state here. And so the state, during the processing of one single block, the state, there's this thing called transient state. It's obviously for performance reasons, we do not go into the Patricia tree or database all this time. During one block, we simply have like some sort of hash maps or something else. And also we use the journal. Journal was introduced around 2016. It's a way to quickly revert the state. So because there are some things like revert opcode, like invalid opcodes or out of gas, so you have to quickly revert things. So that's why there's journal. And at the end of the block, there is something called commit, and then normally what it does, it takes all the modifications which are pending and then applies them to Patricia trees, and then eventually writes them out in the database. So at the moment in the Geth, at least, the logic which does the update of the database is kind of also connected to the Patricia tree. So it's like there's a callback in the Patricia tree which then goes into the database. So when you also have like a node which responds to RPC requests, that these RPC requests normally come into the Patricia tree thing. And then, one of the interesting examples that there is this RPC call in debug namespace, which allows you to query all the accounts which have been modified within the range of blocks. Let's say there's block 10 and block 20. Give me all the accounts that have been modified during this block. And this is very popular for people like exchanges, because if they watch out for the deposits made to, like, imagine how the exchange worked, they would have like hundreds of thousands of deposit addresses, individual for each user, and then they have to tell like whether anybody deposited anything. So they would use that call to query for the accounts that have been modified, and then they will match up with what they know are their addresses, and then they will figure it out. And then because that query takes a long time, they will have to do it again. But by the time they got results, there's already another 20 blocks, right? They have to keep doing it. And if you look at the implementation of this particular RPC query, it actually goes through the Patricia tree. So it kind of reads up the Patricia tree on the block 10, and another Patricia tree on the block 20, and then it iterates over them, and then does the difference. And it's actually quite slow. So now let's look at the. Actually, let's change the order. Let's do this first. So this is what I ended up at the moment in TurboGeth, which is these parts are the same, pretty much the same code. So EVM, there's a transient state, but what is different is that when you commit at the end of the block, instead of writing to the database through the Patricia tree, I actually have the common interface, which doesn't care whether it's a database or Patricia tree. So you can actually write to one, to another, or to both with the same call. And so I try to separate them as much as possible. And there is still one. Unfortunately, there's still one link which I can't remove. It's essentially when you store the account, it has a state root of its storage. It has a root of the storage thing. And it's intrinsically kind of Patricia tree dependent, and that's only one thing which still keeps a little bit of coupling. So otherwise, could be completely decoupled. Anyway, so recently, so before that, this slide actually pictures just one database, but now I separate it in two because I realized there is a big value in separating history and the current state, and I will show you later why. And so there's on the slide of the Geth, you saw there's many trees here, but there's only one tree here. And the reason for that is because TurboGeth currently can only hold one version of the state. It cannot hold multiple branches as the Geth actually can. So if somebody comes with a RPC request, they don't go through the tree because they don't have to. They actually go straight into the database. And lately I started to realize that this database could actually potentially could be just SQL database, right? And then you just use SQL to do your RPC queries. I have not confirmed it 100%, but I'm pretty sure that it might be tried. So then let's look at this thing. So this is, some of you might know this. There is this project called Ethermint, and it's been attempted by people from Cosmos team, Interchain Foundation. So they already have an Ethermint 1.0, which was done before I even knew about it. So, and what they did is they took the Go Ethereum and they did heavy modifications to essentially to use part of the Tendermint stack and to Cosmos thing, or maybe not even Cosmos. Cosmos might not have existed then. So essentially part of Tendermint stack and just replace it and see whether you can actually run Ethereum on top of Tendermint. And the problem with that approach, it kind of worked, but the problem was that you cannot keep up with the changes in Go Ethereum. It's very hard to maintain. So then they asked me to look at potentially what Ethermint 2.0 would look like. And I said, no, we're not going to modify Go Ethereum, we're going to use it as a library. And I remember Peter from Go Ethereum team talked at DEF CON 2, said his talk was like, use the Go Ethereum as a library. And I remember that, it's like, okay, why don't we try to use Go Ethereum as a library, and actually Cosmos also as a library. So the Cosmos has got Cosmos SDK. So I tried to do some digging there. And essentially architecture is like this. So we do read commit. There is no Patricia tree here, so I managed to remove it from here. It was a bit hacky, but I managed to do it without modifying the Go Ethereum code. It required one small pull request, which was accepted in 1.8.11, which does a little bit of abstraction. But essentially what happens now, it's very early stages, but we're serializing to AVL trees. We are not using any of the Patricia stuff. It all goes into Tendermint stack, and eventually it might be using some of the proof of stake that they have. But it's interesting that what this particular piece of work made me realize that I might be able to actually do this with actually using Gethmo as a library rather than as a fork. I need to look at it a bit more, but actually just gave me the idea. So let's look at the other differences. So this was the slide that I already presented, but there is a little bit of change here. So obviously, first of all, I changed the database from LevelDB to BoldDB, and I wasn't able to say a lot about it last time because of time constraint, but I will go into this a little bit further now. So why? So the LevelDB is a database which is called the log structured merge architecture, and actually there are quite a few of them. And the main idea of this architecture is that you have a log, which some people call write-ahead log. So whenever you write to the database, you simply add the entry to that log, and you just forget about it. It's like, and then you move on. So on the background, well, the database has the series of levels, and it essentially runs this what they call compaction, and it just basically rewrites things from one level to another. It tries to compact itself. It tries to, let's say, merge the entries. For example, if there are two entries in a log which pertain to the same key, it will merge them together as it lifts it up with a level, and then if there's a deletion, it will also merge it with the other updates and will kind of clean it up. It's good because the writes are very fast. You know, they're pretty much not on the critical path, but there is a cost for that. To pay for that is, first of all, there's a thing called write amplification, which means that every record that you write in database ends up being rewritten multiple times as it moves up the levels. So then there is also part of it is the read amplification, is that the entry might be located at multiple levels, and you need to do a bit of work to figure out where it is now and what is the current state. And also, just empirically, when I run on this laptop, when I run Geth at LevelDB, it's really noisy. I can hear the noise. When I run TurboGeth and BoldDB, it's very quiet. Although it probably does. I think it's a matter of the background processes which are going on. So the difference with the BoldDB is more kind of traditional B+3 approach. So to remind you, the B tree is essentially it's a tree which, unlike the binary tree, it's got multiple nodes on each level. And the B+ is because the actual values are stored only on the leaves, not on the branches. And so the good thing about this B+ tree is that it allows you to do better atomicity, so you can actually support ACID transactions. Unfortunately, when you want to insert something, you have to find where it's going to go. So you have to traverse the tree, you have to find a place and write it there. Or you also have to, when you read, you also have to traverse. It's just an experiment. The other thing I did in TurboGeth, I tried to replace the predominant workload. So in the Geth, the predominant workload is the random access to the storage. So you use random reads, random writes, and the reason for that is because this is the main reason for that, because the layout of the state is so that these things are pretty random, right? And we don't really exploit the fact that the level DB actually is sorted. It sorts the keys, but we actually use it as a random key value storage, right? So in TurboGet, the predominant workload is instead something called traversal. So we traverse the database. And what I also try to do, I try to batch them up as much as possible so that we traverse as much stuff as possible in one go. Then there is a large transactional buffer as a red-black tree, but actually I'm going to probably remove that because I realized that it might not be needed. I can simplify this. But essentially I had a problem that when I was batching up a lot of updates, it was very inefficient to batch them up in the BoltDB's own buffer. I actually had to introduce my own buffer, and I just picked up some red-black tree implementation and just did that. And as I said before, the TurboGet cannot maintain multiple tips of the chains. So what that means is that if you, let's say that if you follow in the tip, and sometimes you get these little forks this way, that way, that way. So what the get does is that it sort of remembers them. Like, okay, it goes 2 blocks in this way, 2 blocks in that way, maybe 2 blocks in that way. Eventually some of them win, but it doesn't know yet which one. So it remembers them for a little while and then just like goes through one. So in TurboGet, because of the way that the database is organized, I did not introduce the mechanism for doing that. So essentially what it does is just like, okay, so here's the bunch of blocks. If the total difficulty is bigger than I had before, then I will accept them. If not, I'm not going to accept them for now. So it still remembers the blocks. So it doesn't actually do anything until it knows that the difficulty is larger. So that's why it doesn't, it cannot maintain multiple forks at the same time. So when the reorgs happens, it has to go back and rewrite them. But the rewinding, I actually did some tests. It's actually pretty efficient. I wasn't able to test them thoroughly though. So now let's look at some latest data, performance data. So these blue line, this is the time, right, in hours. So the blue line are the days, 24 hours each. And so this is the sync time. I got this idea of this graph from Afri, who is working for Parity, and I really like that. So I started to use that format everywhere. This black line is like a database size, how it grows. It went to 350 gigabytes, is it? No. Okay, maybe something wrong with it, but I think it might be clear. No, actually, no, I remember. This is the version where the receipts are not optimized yet. That's why. In the version where receipts are optimized, it's actually gone down quite a bit, probably 80 gigabytes less. So you can see that there are some sort of inflection points here. So it's where the slope changes. And my theory currently, I haven't verified it, is that it's when the block size is raised, gas limit is raised, or there's some sort of attack, which was here. I already remember like what are the block numbers where attacks happen because I watched it so many times in logs. It's like, okay, so now it's coming, like 4.44, like, yeah, so, and of course, because this only displays the blocks, there are actually more transactions in the blocks here. And the database growth here is largely driven by the receipts. So now let's look at this is the memory. So the yellow bits are the heap. The blue, like the green bits, is the number of Patricia tree nodes. And here, this is another thing I've done differently. So in the get, currently there is no way to restrict how many Patricia tree nodes there are in the memory. So it's done in a direct way by saying how many generations of the tree nodes can survive. I think it's 128. So what does it mean? Every time there's a new block committed, the generation is passed. So if any Patricia tree node which hasn't been accessed for 128 blocks, it gets removed from the tree. which means that you don't really know how many tree nodes you were going to have, depending on how, you know, how active the processing is. So what I've done is that I've introduced this linked list, which basically goes through all the Patricia tree nodes with some overhead, but I actually count them. I count how many they are, and I have this LRU sort of cache of them. So I have a limit of how many they can ever be in the memory. I was hoping that I would be able to get a nice correlation here between this and this, but it hasn't happened yet. There was when I was at Toronto, there was a memory leak, then I fixed it, and I thought the graph would actually just kind of go like this, but it didn't yet, so there is still so there's still some work in there. Now, this is probably the most interesting part for now. So 260 gigabytes, I need to remind you, this is the archive node, which basically the archive node is the node which has expanded state for the entire history. What does it mean, expanded state? It means that for each block, it has the record of what each account was at this block, like what is the value of each account, and what is the value of each storage entry. And of course people sometimes say, oh, you know what, these, like all the nodes has all the information. Yes, it only takes 44 gigs to store all the bodies of the blocks, but you can't query, right? So the difference is that you have to somehow expand it, pre-process it in order to be able to query. So that's why I say that if you compare this, you compare it with the archive nodes, whatever, like, I think they're currently over terabyte in other implementations. So, before I did this, so the previous versions of this did not separate history of accounts and history of storage from the actual storage. And this is one of the first time I did it, and I came to interesting conclusion that, no, actually, well, I'll show you later. So essentially, the one bit which is this is the bit which is the specific to TurboGet. It remembers for each block which keys have been changed in this block. And I don't know, maybe I'm going to optimize it, but this allows you essentially to do very quick rewinding because it knows which keys to delete. Because like, okay, so I have to rewind 10 blocks back. I actually first fetch the set of the keys that have been updated and just rewind it, completely delete it from the database. I need to think maybe I need to change this somehow. So you can see receipts are quite large. I have optimized them. They used to be like 100 gigabytes. They used to take like a third of this stuff. And the reason why receipts are so large is that, well, before the optimization, is because receipts actually store a lot of redundant information. They store block hashes, transaction indices, although this all stuff is already provided when you actually query them. So when you query the receipt, you already say, I want a receipt from this block hash, from this transaction, from this index, but then this information is get repeated to you back. It's very easy to optimize, very easy to remove. And then another thing is that it stores the logs. And again, the logs, again, repeat all the same information, block hash, blah, blah, blah. And also there's a lot of the empty logs, which is 0. But there's no kind of compression. Because the logs contain so what I've done is that the logs contain Bloom filters, and I basically decided not to store Bloom filters at all. I compute them as when you query the receipt, you just compute the Bloom filter. It's quite easy. Like, it's not like your block is super large and Bloom filter takes like 3 minutes. It just takes like maybe like half a second to compute the Bloom filter. I haven't measured it yet, but anyway, so that's pretty much it. So you can see it accounts 3.44 gigabytes. This is the current accounts. And storage 6.21 gigabytes. Remember these numbers, actually I will repeat it and compare it with the history, right? So it's actually not that bad. The state is not that large. So what we have left till I can actually get some workable version, at least from my point of view, I need to test reworks. I need to fix some of the RPC API calls. Potentially add support for retested. This is what Dmitry was presenting yesterday. But even then, the database layout is going to change, pretty much. I'm pretty much certain of that. So it's not going to be like, you have a first version and I will support backwards compatibility. No. There will be no backwards compatibility, at least for because it's too much burden for me to do that. So very recently I started to look at light clients. I have completely ignored them for several months because I thought, I can't really hold all these things in my head. And only recently I started to look, can I actually support light clients or not? Because I had this fear in the back of my mind, maybe I won't. And so we see here, there's the ETH, there's the LESS, two protocols, which are both protocols which are served around the peer-to-peer networks in Ethereum. And they have some common commands. For example, you can first a handshake, you can retrieve the block headers, block bodies from each other. So the bit which I cannot do now is this, the third line is called the get node data. This is unfortunately specific to Patricia tree, which is something that I wanted to avoid. So, and this is used by fast clients to retrieve the current state, and that's the reason why I cannot support fast clients, because I just simply don't have this information. And it's also not used by the light clients, I suppose. So we can do receipts pretty easily, we can do block hashes easily. So one thing that I cannot really do very easily is the proofs and actually the proofs only. So this is fine. This is the helper tree proofs are essentially the proofs of the Bloom filters and proofs of this thing called CHT, which is the canonical hash tree. But they're pretty easy. So I will have this information. So the only problem that I would have is this one and the get node data. You see there's red things. And the reason why I would have problems here is that if the light client or the fast node queries the get node data or proof for current state, I will be able to respond because the current get has the current state at the moment. But if they're a little bit behind, let's say that they're like 3 blocks behind me and they will ask for it, I don't have it anymore. I already moved on. I've rebuilt my Patricia tree because I only have one for current node. So in order to solve this particular problem, maybe we'll do some compromise. We will store some of the Patricia trees from the past a little bit for like maybe 10 blocks. I mean, depending on how, so this is like, if I really want to support light clients, I might do that. I might just like, okay, I'm going to store 10 block history for the Patricia tree, but then I just remove it. And if somebody tries to ask me the history back then, just tough luck. I'm not going to do anything. So that's my current strategy. So, okay, now this is the interesting thing that I haven't implemented yet. These are just ideas I'm just going to throw at you. And some of these ideas are just appeared a couple of days ago. So we had this conversation with Dmitry from testing, and he said to me, like, did you actually try to put everything in memory? Like, the whole thing in memory? Like, what happens? And we did actually try that, but although it wasn't a very scientific experiment, in the early days of Turbiget, what we actually, with some people from, so I think there was a guy from either MyCrypto or something. So basically what we did is that I did a little hack of Go Ethereum and we replaced the level DB with the Redis. It was surprisingly simple because it's probably like a praise to the Go Ethereum team. It was so well abstracted that actually it took me 2 hours to completely replace the level DB with the Redis, maybe even less. And then just like, okay, let's try it. And so they run it. I didn't have that machine with so much memory because it needed like 400 gigs of memory. But they had it somehow and said, okay, let's do it. And so he said, it was super fast, well, not super fast, it was probably 2 or 3 times faster than Visual Sync, but unfortunately he never gave me the logs, although I asked several times, and I didn't get to repeat this experiment. But then when I looked again at this diagram, I said, look, 6.21, 3.44, what is this sum? It's about 10 gigabyte. Actually, you could afford to store at least the current state in memory. And this is what matters for most of these Patricia tree recalculation. This is where the most time is actually spent during the sync at the moment. Right. And this is how I'm going to do this. Well, this is the current plan. So because the BoldDB, one of the features that I didn't mention of the BoldDB that I really like is that it has the very little code. I was able, within 2 days, to completely look at read the code of VoltDB, pretty much completely understand it, and then start modifying it. This is what I like. I wouldn't be able to do it with LevelDB. So I basically understand how the VoltDB works pretty much inside out. I already done a few modifications in it. So, and one of the modifications, which should be pretty easy to do, at the moment the LevelDB, the VoltDB, the way it works, it uses this memory mapped file concept, where you have a large database file in disk, and you do memory mapping, and whenever you access something which is not currently in memory on the background, the operating system would swap it out with the disk. It's very convenient, and that actually has the advantage that you could actually utilize the memory that was otherwise not used by other processes. So you can actually access the memory that is floating around the operating system, which is cool. So what I'm going to do, you see that little 2 slices? I've taken them out of here, because this is still going to be on disk, but I'm going to create another option in VoltDB, which will allow you to not have a memory map, but simply memory. It will look like a VoltDB, but it will be VoltDB on memory. So all the pages will be just stored in the memory. And they will be loaded on the startup and stored on shutdown. And then we'll see how it works. And so if this gets corrupted, what we're going to do, we still have so history actually has you can reconstruct. So currently the way the history is done, that you can actually reconstruct the current state from the history by just looking at the latest bit. And there's already a query for that, so there's shouldn't be a problem. I haven't tested it yet, but I will very soon, when I'm coming back and have some time to code. So next thing is that this is the idea I started to think about maybe a month ago, or maybe a couple of months ago. So the idea is that, you know, when you have VoltDB, you got LevelDB, but so what these databases give you, they give you a one-dimensional kind of inherent index. So they give you like a sorted key. But what you really want, you don't really want sorting in one dimension. You need it at least in 2 dimensions. And then you have to start inventing all these little ad hoc schemes for jumping around the database, like, okay, I'm going to have a timestamp, and then just have a snapshot. And then it becomes a bit, first of all, it becomes a bit messy. It's not very transferable. So I thought, okay, so maybe I was actually familiar with graph databases before, and I thought, you know what, I always wanted to try if we could put the Ethereum state on the graph database. And the reason why I like this idea is because, not simply because you can create arbitrary indexing in that, like whatever you want, but also because you can overlay additional information onto the graph. For example, if one day I decide to support fast clients, and this is all in the graph, I say, okay, I'm not going to store the whole history of Patricia trees, but maybe I'm just going to store once every 1,000 blocks. And I will just insert some Patricia tree hashes in there, so that it will be a trade-off, so I will reconstruct. It will be quicker for me to reconstruct it. Or maybe somebody wants to try the ERC20 tokens, and they want to overlay it to the database here, so that you can have a special RPC queries for that and stuff like this. So it will be quite interesting, because then you can latch on to specific block numbers, to specific accounts, which are all represented as a graphs in the node. So here, this picture shows you, so here we've got the accounts, so here we've got the block numbers, and so at the moment when you query some state of the database, state of Ethereum at the block 339, this is actually what you're querying. So this blue line that I show here, I had to implement this in VoltDB by using some, what I call the guided traversals. I didn't really like it. The code is a bit ugly, and it's not very fast in the end. So what we could do is that if we explicitly mark it with these edges in the graph, we might be able just to traverse it directly. And then another thing, and usually the graph databases, they support things called node types, edge types, so we can create one type for the block, for example, and then the queries, normally the query languages come with the graph database, they support discriminating for the types. So, and remember this bit that I was talking about, the changed keys, the thing that I keep around in order to make fast rewinds, and I didn't really like it because it takes so much space. So what we could do here is, actually I forgot what I was going to do here. Oh, yes, we actually introduced one node type per block. So basically nodes will be marked by a certain property or node type depending on which block they appear. So all the records will basically be marked by which block they belong to. And then it becomes pretty easy to rewind, because we can just query for which nodes are, so which records belong to the nodes after 339, we're just going to remove them, like in one query. And so I started to have a more interest in this after this event. So very recently, this is actually not a project logo, I have just put it together for them. So they don't have a logo yet. So NSA has recently open sourced the graph database. They didn't say what they were using it for, but it's actually a very interesting project. I started to look into it, and underlying storage is called LMDB, which is Lightning Memory Mapped Database. Essentially, it's another B3+ database, and the architecture of the Lemon graph is that, well, they claim it to be super fast. It's written on C with some Python bindings at the moment. I have managed to install it and did some tests, but I haven't figured out how to map it into the Ethereum state. But one of the ideas here is that it's essentially it's append-only database. So you never actually delete stuff. You keep appending it, and this probably does make sense for their use cases. It has this, it's called a log database. So whenever you add the entry, it goes into the log, and it acquires the log ID, and this then log ID is they ever incrementing, and this that log ID is then getting referenced anytime you create some kind of object. So when you create, let's say, a node in a graph, it gets added as the log entry, and then there's the entry in the index, which connects that node ID with a log ID, and then you can connect the edges with the corresponding sources and targets and stuff like this. So these are the indices that they maintain. So indices of nodes, edges, properties. This allows you to go from the edges to the sources, or the other way around. These are the transactions. So actually they support transactions. So they also have a bit of a clutch, which is the key value store. They also have a very clever mapping of, like, let's say if you have a lot of repeated information, which we actually do have in the Ethereum state. Like, let's say if you look at the storage of accounts, you probably find a lot of addresses, because a lot of them are tokens, right? Like addresses here, addresses there, like all over the place. And they probably lots of replications there. So you might take some advantage of that and compress it somehow. So they did something interesting, which is very simple but interesting. So they have these scalars, which could be like property values. And so they give each scalar an ID, which increments. And they have two indices, one which maps from scalar ID to actual byte sequence. And in order to map back, for example, you have a new byte sequence which you need to decide whether it's a new one or it's already existent. So they do also CRC32, they don't do SHA-3. So it's much quicker, this one. And then it maps to the list of potential scalar IDs, and then just quick. So it allows them to actually store each value once. And one of the interesting features of this database is that you can always have this historical view of the database, like a snapshot. So what did my database look like at this point? And the reason why they can do it is because this log structure, they always have this. So what is the state up to the log ID number this? And then you just look at it, and you look at as if the database was there. And that might be potentially very useful for historical queries. Again, this is like, yeah, actually this is the last slide. And I welcome any questions. And thank you for your attention. Yes, please.
I'm loud. I don't know if I need a microphone. We're recording. Okay. Thanks, Alexey. Great presentation. Learned a ton about TurboGet.
I'm curious about downsides, right? So you talked a little bit about it in the context of like you don't get light client support out of the box. Are there any other like trade-offs or downsides to sort of the approach you're taking?
Yes, so the light client support might need to be bolted on, yes. Then fast sync is very hard to do, probably impossible at this stage. Another downside is that there potentially going to be a slow startup time. Because basically you have to, because you don't have a Patricia tree, you have to rebuild it on a startup. I had this a bit of a solution where I store like first million, like a top million nodes from Patricia tree, but now I might throw it away because when I separated the current state and the historical state, I realized that loading up the state actually becomes much faster. I might not need that little hash file. So that's another thing. A slow startup potentially. I'm still not sure about reorgs. I might actually find some blocker there. I might need to do some more stuff. It's another thing, and that's why I'm saying is that I'm not 100% sure it's going to work. It's probably 95% sure it's going to work, but not 100. Yes. What are the downsides? From the technical standpoint, I don't think there are any more. Yeah. Maybe something I can't think about it now. Yes?
So you presented a lot of results about reducing the database size. Another goal, which you outlined in the initial blog post, was to reduce the latency of disk I/O when processing transactions by reducing so it wouldn't require traversing the tree to do like an S load or to read something from the
yes,
state.
so this is, I forgot.
Because the bottleneck is disk I/O, so if you widen that bottleneck, then we could in theory raise the block gas limit. How's it going with the
so basically, one thing I forgot to mention that actually because there's a lot of details that I actually just forget to mention. So one of the things that's also different is that when transaction is executed, for example, in get, if some account or some storage value is not in memory, it will always access it through the Patricia tree. So it will have to load it up through this expansion process. In TurboGet, it doesn't do that. So it looks in the Patricia tree. If it's there in the memory, then it uses it. But if it's not, it doesn't do expansion. It just goes straight into the database, do the key value lookup, and loads it up in one go. And when I look at the current profiles, I was worried that this could be like a noticeable thing, but I don't even see it anywhere in the profile, so it actually a very insignificant cost. In terms of the latency of transaction, I now remember I had this idea, which I haven't implemented yet, is that so when you see the transactions in a transaction pool, you kind of can get the idea which transaction will happen in the next block. I mean, roughly, right? You can sort them as if you were a miner. You can sort them up by the gas price, and you see, so probably these transactions have a very high chance to be in the next block. And so what you do then is that, I'm going to heat up the paths in my Patricia tree or whatever, just in anticipation for those. I'm going to prime my caches. And with a very high probability, you will actually be right. Because when the next block comes, you don't actually need to do any disk I/O. You're ready for that transaction. And this is what, this particular thing would be very important for miners, for example, because one of the reasons there's actually two reasons why miners don't like get at the moment. So the first one is the Stratum support is missing, and it's pretty important for them. And second bit is that they claim that the Geth cannot keep up with the tip in a very stable manner. So it very often falls behind. There is no data to support this claim, but so in order to alleviate this, the idea is to essentially preload the caches as you look into the transaction pool, because the information is there. And another idea I had, which is a bit more crazy, which essentially is like using some sort of machine learning for better cache strategies. Because basically, the cache strategy which we all use everywhere is the LRU, list recently used. We are assuming that whatever has been recently used will be used again, but maybe that's not, maybe this is not the right strategy. Maybe that's not by far the optimal one. Maybe you can actually learn from the past what is the current strategy because you do have a past, you have a benefit of hindsight. But this is kind of such an idea which I haven't even started.
Did you try RocksDB, which is a fork of LevelDB for flash storage? So I suppose the write amplification part is somewhat addressed, and it's used by Parity as well.
No, I was aware of it. I also was aware of another database called the BadgerDB, which is kind of similar. So they took the LevelDB, they took BallDB, or they tried to do something between. No, I didn't honestly do that for no specific reason. I I just chose the BallDB and I decided to kind of try to torture it until I decided it's too bad, or and I didn't swap. But for now, it actually works. So I didn't find any very significant flaws in the BallDB that would prevent me from using it. And as I said, I understand it. It's very easy to learn the code. Oh, well, thank you very much then. Any more questions? Oh yeah, I think there's one question there.
What's your end goal? Is this to be, you want this to be merged back into Get?
So that's an interesting question. We actually discussed it with not really, we didn't discuss that particular thing with Felix yesterday. He was around here. And I told him that I'm totally happy to merge things back, but at the moment I can't do it because it's just impossible in terms of my time to do that, to prepare. Because essentially everything that I've changed is actually would require active work to be backported into Go Ethereum. So I can't just do the pull request out of my repo to there. I have to actively work on modifications and do lots of things. So although I'm happy to do that, I don't have capacity at the moment to do this. So the end goal is to see where it's going. And I don't want to do this for like 10 years, of course. I would like to get it to a certain stage where either it doesn't work and I just drop it, or it works and it solves somebody's problem. And if I'm still happy to continue this, I will do it, or otherwise I will get it acquired by somebody else. And then obviously I don't want to do it forever. So, because there might be something interesting here. But I'm pretty happy to, when it gets to the stage where I know it works, somebody will surely come up and say, we want to maintain this project.